Good morning. Thank you for participating in Morehead at Home Skywatching, hosted by Morehead Planetarium and Science Center. My name's Amy Sale. I'm an educator at Morehead. We are a unit of the University of North Carolina at Chapel Hill, located on campus. We also work throughout the state through a number of outreach initiatives like our mobile lab vans, summer camp programs, and the annual North Carolina Science Festival. Our mission is to help people better understand science, technology, and health, and we do this through engaging learning opportunities like this live virtual event. We're happy to have you here today for our session on the James Webb Space Telescope, and Nick will get us started.
Hey, thanks, Amy. Welcome, everybody, to Morehead at Home Skywatching. My name is Nick Eakes. I'm an educator at Morehead as well, and we're excited you're here with us today. As Amy mentioned, we're talking all about the James Webb Space Telescope. If you're a space fan or keep up with space news, you might have heard this name tossed around for many years now, but we're going to try our best to give you the story of what this telescope is, some of the history behind it, its function, what it intends to do, and maybe get you a little bit excited about kind of a new piece of technology out there in space. So we're going to be sharing a number of things with you today, some images, some websites, YouTube video. So any relevant information that we share will be put into the chat. So if you need to access it, you can check there. But we also want to encourage you to ask us questions. Since we can't talk face-to-face, the best way to ask us questions is to use the Q&A function on your screen. For most of us, if you're on a computer, it should be at the bottom. And if you're on a phone, I believe it's at the top. But either way, if you're curious about something during this session, type it into the Q&A and we'll try to take some time at the end to answer any of those questions. But Amy, I want to know, what is this James Webb Space Telescope?
Yeah, can we take a look at it? I think you've got an artist illustration of it. So James Webb Space Telescope, you will not be surprised to learn, is a telescope that will be launched into space. So it's not there yet. The plan is to launch it on Halloween next year, 2021. This telescope will be a successor to the Hubble Space Telescope. It will have more sensitivity, and unlike the Hubble, it will be optimized for infrared wavelengths, and we'll talk about that more later. But the bottom line is that by studying infrared, the James Webb Space Telescope is going to be able to look really far away, which also means looking really far back in time to see when the first stars and galaxies formed. And it can also peer through dust clouds to help us study stars and planets that are forming today. And it'll be able to study the atmospheres of exoplanets to figure out if they might be habitable or not. And one thing I find really interesting about the James Webb Space Telescope, Nick, is that it's got a North Carolina connection.
It sure does. So James E. Webb was the second administrator of NASA. He served as NASA administrator from 1961 to 1968. And if those dates ring a bell for you, that was a pretty consequential time for our space administration. He oversaw most of the Apollo program. The cool thing is James Webb is from Granville County, North Carolina. His town of birth is called Tally Ho, which, you know, even as a North Carolinian, I wasn't 100% sure where that is. It's just a really cool name, but it turns out it's only about 25 miles northeast of here, Chapel Hill. And James Webb is a UNC Chapel Hill graduate as well. He got a degree in education. So we're pretty proud of this hometown boy. There's even a high school in Oxford, North Carolina, named after James Webb's father, who's the superintendent of Granville County Schools for 20 some odd years. So the Webb name has a connection to our area of the state. So if you're watching from North Carolina, it's a pretty neat thing.
Okay, so let's learn more about this telescope. We've got another image of it in the clean room at NASA Goddard, and you're kind of seeing it face on here. The big gold parts, that's the telescope's primary mirror. So many of you may know that the purpose of a telescope is to collect light, as much light as you can. And how much detail the telescope can see is related to how big that area of that big primary mirror is. A larger area will collect more light, which is good. It's kind of like if there's a rain shower going on and you have a bucket outside, the bigger the bucket, the more water it will collect. So the bigger the area, the more light. And this mirror is huge. It is more than 21 feet across, which is gigantic for a space telescope. But that's the kind of thing that you need to capture light from really distant stars and galaxies in the universe. And Nick, you told me you have actually been to this room.
Yeah, so this is the NASA Goddard Space Flight Center. It's in Greenbelt, Maryland, just a little bit north, I guess, of DC. And back in 2014, I went to something called a NASA Social, which is a way for people who do lots of social media and stuff like that to get kind of a behind the scenes tour at NASA facilities. And we got to go see the Webb telescope inside this clean room. You see that I'll try to point it out here on the screen. All these scientists are in their bunny suits. The clean room is really important because you don't want to mess anything up about this very expensive piece of equipment, and you don't want to accidentally take anything into space from here on Earth that you're not supposed to, including germs and bacteria and things like that. So when people do work in these big clean rooms, it is really locked down, and we even had to put on bunny suits just to go observe it. But that was back in 2014, 6 years ago. And a lot has happened since then with the Webb telescope. So I can even show you another image here that I think is really impressive.
Oh, I love how this also gives you a sense of the scale. You can see the person standing maybe in the sort of the center lower left, lower part of that image. And you're actually seeing only a little bit of the mirror. You're seeing 6 of the 18 segments of the mirror. And you might be wondering, why is the mirror in pieces? I mean, when you have a mirror in, say, your bathroom, it's probably just one piece. Well, the issue is this mirror is so big that it's really too big to launch into one piece on a rocket. So they have to divide it up into segments that can be folded. And so each segment is a few feet across, and they fold it so it can fit into the nose cone of a rocket. And it's kind of similar if you've ever seen a dining room table that's called a drop leaf table. So it's got sides kind of on the ends that can be folded up or folded down to make the table bigger or smaller. That's kind of what this mirror is like. It can be folded to be able to fit into a rocket. And if you study one of these segments, you'll see there are 6 different segments. Count the sides of one of the segments. Nick, how many sides do you see if you look at one of the segments?
I see 6 sides on each segment.
Yeah, I see 6. So that's called a hexagon. And when you put hexagons together, it fits together really nicely. You can see that there aren't any gaps, which is an efficient shape to use.
Yeah, along with being a feat of astronomy, the things this thing's going to be able to see, it's also a really great feat of engineering to design it so precisely and test it out before it even gets into space to complete its mission. And that kind of hexagon configuration is one of those things. Amy also mentioned this chamber that you see the segment of the mirror in right now is a cryogenic testing chamber, which means it's designed to get really, really cold. And if you think about it, it is pretty important to test these things that are going to go out into space for extreme temperatures because the vacuum of space is very, very cold. It's cold out there in space. We want to make sure all the electronic components and things like that still work. So we do a lot of that testing at really, really cold temperatures here on Earth as well. But we'll mention in a little bit, this telescope has an interesting balance because at some points, one side of the telescope is going to be incredibly hot, and at some points, the other side is going to be incredibly cold. So there is kind of a balance to strike when you're dealing with things that are, say, facing the sun out there in space. But another engineering challenge that we kind of thought of was how in the world do you pack this thing up and move it to its launch site? And it turns out that the folks at NASA and Northrop Grumman have thought about this. What you're seeing here is what they call a mobile clean room. So imagine that big warehouse where you have the thing unfolded and you're working on individual pieces of it. Well, to transport it, you need to make sure that standard of clean is met. So they basically put it in a giant bag. I don't know if there's a cleaner way to say that. They wrap it up and transport it safely. So this mobile clean room is kind of like a big sanitary Ziploc or something like that in order for the telescope to be able to move from place to place. So where they're moving it to, they're moving it so that they can do final testing, and then eventually next year, they're going to put this thing inside of a rocket to launch. And we wanted to show you a little schematic of how this is going to work and talk about a couple of interesting pieces of this, because this is actually launching on an ESA rocket, the European Space Agency. This is called an Ariane 5 rocket, and you see some of these cool ESA logos and lots of countries' flags. That's because this whole project is a partnership. Even though NASA and Northrop Grumman, the contractor, have worked on the telescope itself, we're working with other nations to be able to launch this thing. So as you can see, maybe start with the middle piece here. You see the telescope itself folded up into the nose cone of the rocket. And that translates to being just the top portion. All that propulsion and fuel and good stuff happens in the bulk of the rocket. So we need to be able to lift this very heavy thing up into space. And maybe this gives you a little bit better sense of how it's all folded up. I always think these schematics are pretty cool. So you might already be getting excited about this launch happening. You do have to wait until Halloween of next year, fingers crossed. But what we thought we could do at least is share a video with you. It's about a minute long that shows a little bit more about this process of how it's folded up and how we think it's going to launch. So give me just a moment and I'll bring this up for us. This is a YouTube video, which we can give you all the link to before too long, but we're going to play it. It has a little bit of sound to it, but we might narrate a little bit over as well. So fingers crossed for no ads here, folks. Here we go. What you're seeing is kind of how they put it into that mobile clean room in the larger Goddard clean room. It's definitely an operation. Pretty cool. So I'm going to go ahead and close this out for us. Hopefully that gave you all a good look at maybe what that process will look like. And I think one of the most fascinating parts was at the very end. It was really quick. You got to see how this thing is going to unfold. I know for the scientists who've worked on it that is a nerve-wracking thought. But again, I think it's still a pretty amazing feat of engineering. We can very precisely get something into a configuration so that it can get safely into space, and then it can unfold and do its beautiful work. So I know we wanted to talk a little bit about where it's going as well. There are lots of pieces to this puzzle. The launch hasn't happened yet, but we do have a plan for where this telescope is going to operate. And it's very different than, say, the Hubble Space Telescope. A couple months back, we did a session all about Hubble. We still love Hubble. Hubble, should still be operational on some level when Webb is up there. But we like to say it's the successor. The Webb is the successor to the Hubble telescope. So, and you'll see here in a moment why it's kind of in a different place. Hubble is in what we call, I guess, near Earth orbit, Amy, or is it even
low Earth orbit, just a few hundred miles up, about 570 kilometers. And if you're looking at the top left of your screen, obviously that's a depiction of the Hubble Space Telescope. It is not that big relative to Earth, so this is not to scale. Also, the moon is not that close to Earth. It's not to scale.
Right. And I think they just kind of zoomed in on these things to give us a sense of just how far away Webb is going to go. So, yeah, I think this is helpful to us. Hubble is kind of close to the Earth. The moon, it took astronauts a few days to get there, about 250,000 miles away, if you need to do a little bit of conversion there. But Webb is going to be placed eventually all the way out at the second Lagrange point, which is what this kind of diagram here in the bottom left shows us. The simple way to describe this is that there are certain points in orbit around the sun where really useful alignments happen. And in this case, L2, which is about 1.5 million kilometers away, gives us an alignment so that the sun shield of the Webb telescope can block the sun, the Earth, and the moon at any given time. And I know that is kind of a tricky thing to think about, but maybe in this image you can see if we're way out here orbiting around a point, the alignment works so that you can kind of aim better and not have any of that extra disturbance or distraction from sunlight or from Earth and the moon being in the way of whatever you're trying to image. It's a nice, stable place to orbit and do really good observations. There have been satellites sent out to L2 before. If you've ever heard of the WMAP satellite or the Planck satellite, it's not the first time we've sent anything to this point, but it makes the mission a little more tricky because unlike Hubble, there's no way to service this telescope. You might know that in the early days of Hubble, astronauts from the International Space Station had to go out there and fix parts of it. They were able to go physically service it. There is no service plan for the Webb telescope once it gets 1.5 million kilometers away. So I know that's kind of scary in case something goes wrong, but that is one of the big differences.
And also the Hubble Space Telescope, you can sometimes see it pass overhead. I was with some folks on Jordan Lake, and we saw a visible pass of the Hubble Space Telescope because it's only in low Earth orbit. It was launched by the space shuttle, serviced by the space shuttle, but this is getting launched by a rocket, so we can go pretty far away and orbit the sun. And we've got an image that shows a little bit. Nick has been talking about this sun shield. So you can see in this image that if you look at the lower left, it talks about the light from the sun. So here's the issue. This space telescope is supposed to be looking at infrared, which is a type of light that's essentially heat energy. And so if you want to measure the really faint heat signals from something really far away, you need to not have your scientific instruments and your telescope mirror swamped by other sources of light and heat, such as from the sun or even from Earth and the moon. And you've got to keep things cold. So it's got this giant sun shield. It's sort of like the telescope has its own parasol or umbrella to block light and heat from the sun, Earth, and the moon, and also to keep the scientific instruments really cold. This sun shield is basically the size of a tennis court, and it has 5 super, super thin layers that can reflect the heat from the sun. And now we've got a question for you all. Why do you think they're launching this thing into space? I mean, think about all the trouble that is being gone to here. We've got to have this mirror that can fold up so it can fit in a rocket. Then it gets launched into space. It's got to unfold right. It can't be serviced. Why don't we just put this thing on Earth? There's lots of telescopes on Earth. Okay, so give us your best guess. You've got 3 options. Why will the James Webb Space Telescope be launched into space? Is it because all the good places to put telescopes on Earth are already taken? Is it because Earth's atmosphere makes it hard to study some types of light? Or is it just because who doesn't love watching a good rocket launch? So give us your best guess there. And we'll give you a few moments. So we know that some of you are watching with other people, so you may need to discuss what you think the best answer is. Let's see what you all say. Oh my gosh, Nick, everybody got it. Because Earth's atmosphere makes it hard to study some types of light. Yes, that is it. This is an infrared telescope for the most part. That's what it's optimized to do. And Nick's going to explain more about what infrared light is. But the thing is, basically anything warm generates heat energy that's infrared radiation. And the Earth itself is warm. Humans are warm. We actually emit in the infrared. So you can't have this telescope on Earth for it to be able to do its job. It's got to be launched into space.
Yeah, the way I think about it is if it's in space, it's just going to give us a much clearer picture. There's going to be less interference. There's going to be less noise. It doesn't mean that telescopes here on Earth can't do really good things, but for this specific purpose and looking in infrared light, it has to be in space. So let's talk about light.
And Nick, we've got a question. I don't know if we want to ask it yet.
Ooh, yeah.
How
So
much do we want to give away before we ask the question?
I think we can help you out here and ask the question at the same time. Maybe looking at this chart will help you answer it. But the question is a true or false question, so I think y'all should be able to do this. The question is, there are types of light that the human eyes cannot see. True, false, or I'm not sure. And I think I totally helped you here by putting this big chart on the screen. But give us your idea, because when we think of light, we think of bright things, right? We think of a light bulb. We think of the sun. Is that the only type of light there is? Are there types of light that the human eyes can't see? We'll give you just a minute to try to answer those.
All right.
You're
wow,
exactly
everybody's
right.
awake here. Yes, there are types of light human eyes can't see.
Exactly. So I might have spoiled it for you by putting up this kind of image of the electromagnetic spectrum. That's what we call this whole range of radiation. Yes, visible light, as the name suggests, is light that we can see with our eyes. You might be familiar with Roy G. Biv: red, orange, yellow, green, blue, indigo, violet, the colors of our spectrum, the colors of the rainbow. That is all encompassed within visible light. But the interesting thing is there are still changes in the wavelength and frequency, some science terms for you there, even within the visible spectrum. But as you can see, if you move to longer wavelengths, which means lower frequency and lower energy, you move into the infrared part of the spectrum. If you make those wavelengths from crest to trough of your wave even longer, you get into microwave and radio waves, which we know have applications here on Earth, but you know that you can't see them. If we could see radio waves and microwaves and infrared and for that matter, ultraviolet, X-ray, and gamma ray, our field of vision would be very full of things all the time. So the point is, these telescope instruments are able to see things that our eyes can't see. And that's pretty helpful to us because it gives us a more full picture of what's actually out there in space. But as Amy mentioned, that infrared energy, we can often feel it as heat energy. So that's a good connection for you there. At the very least. So let's talk about maybe what this difference looks like when we see it in terms of a picture from space. So we're going to share a website with you. It's a nasa.gov website all about light. And I'm just going to kind of bring it up here. Really cool web page. You see, this is the Hubble Space Telescope web page. That's not to, confuse you too much between Webb and Hubble. It's just Hubble has a really good breakdown of what we can see and why these space telescopes are useful. Because check out this chart. It might look kind of familiar. Everything's actually flipped around from the one that I just showed you. So the shorter wavelengths are over here on the right. The longer wavelengths are over here on the left. And this shows us where Hubble views. It views into the infrared a fair amount, all the way up to UV. So lots of those images we've seen from Hubble are outside of the visible spectrum. They're different than what our eyes would see. But the way I like to imagine it is that the Webb telescope, for the most part, is going to be shifted to the left here. It's going to see more infrared. And let's look at what a difference that makes. There's a really cool example here of a Hubble image. This is the Eagle Nebula. I'll show you just all visible light. Probably a very familiar picture to you. You see these big clouds of gas that kind of make what we call star-forming regions. You see the light from some stars in the background. You see some more diffuse gas glowing. It's a beautiful image in visible wavelengths. But watch, this website's really cool because you can drag the slider. Watch what happens as we look in the infrared.
Wow. Nick, I'm noticing stars I couldn't see before.
Yeah, so you can kind of see the structure of that gas, but as Amy mentioned, I see a lot more stuff in the background. And that is why it's so useful to look in the infrared. You can see through a lot of gas and dust and kind of clear up your picture a little bit. Of course, these images have a lot of layers to them, but you can pretty starkly see the difference between the visible light and the infrared light.
Wow,
And
I'm feeling like my human eyes are missing out on things, just being
I
able to
know
see invisible.
there's so many cool examples on this website. We want to encourage y'all to try it out yourselves. This is the Lagoon Nebula. Same thing happens. You see a lot more stars when you can kind of push your way through that gas.
And stars form in clouds of dust and gas. So by having an infrared telescope, you can see through and see stars and planets as they're forming and help us understand more about how stars and planets form. There's another issue too, which is the universe is expanding and objects that are farther away are moving away from us faster. And there's a Doppler shift kind of thing that happens. Like if you've ever heard an ambulance siren as it's moving towards you, it has a certain pitch, higher pitch, and then as it goes away, it's a lower pitch. The wavelengths are being stretched out as things move away. And so things that were emitting light in the visible or ultraviolet, they're really far away, moving fast away from us. The wavelengths get shifted into infrared. And so an infrared telescope, like the James Webb Space Telescope, will be able to see the light from objects that are really, really far away from us. We're looking way back in time because it takes a long time for that light to reach us. And so it can help us understand more about the very early universe. So the universe now is 13.8 billion years old. James Webb Space Telescope will be able to see things so far away that it might be able to see as early as when the universe was just 100 million years old, which I know sounds really old, but that's like practically a baby when you're 13.8 billion years old now. So the telescope will help us study stars and planets that are forming now, and also the earliest formation of stars and galaxies. And that's what studying in infrared light will do for us.
Yeah, I think that's such a beautiful thing because these space telescopes, along with being our eyes in the skies, they just expand our view. They expand our understanding. They help every type of science get a clearer picture of what's going on in our universe. I think it's a pretty magical thought to be able to look farther back in time, get clearer pictures of new stars forming. I'm really excited for it. So we hope that it's going to discover lots of things, maybe new exoplanet atmospheres, new planet forming regions, new beautiful images. You know, we hope you're getting excited about it too. I know it's something like 13 months away right now, 13 or 14 months away.
Yeah,
So
we've got another picture of it that I thought was kind of cool. It shows, this is not the actual telescope. This is like a full-scale model of it in a city that some of you may know or have been to. This is Austin, Texas. I actually lived in Austin for a little while, and unfortunately not when this full-scale model of the James Webb Space Telescope was there, because it looks really cool. And again, it's going to launch on October 31st, if all goes well, 2021 from French Guiana, which is in South America.
yeah, we didn't mention that. Part of that ESA partnership is that this is not launching from Florida or something like that. It's launching from an even more remote and purportedly really safe location as far as launches go. Not a very big population. It's free from a lot of the risks that we have at some launch sites in the United States. So it's kind of exciting too. But we obviously could talk about the James Webb Space Telescope for hours and hours. We know y'all have some questions for us. So what we'll do is take our last couple of minutes here to try to answer those. We appreciate you looking at all of our fun images and stuff like that.
Yeah, so Nick, while you're taking a look, there's one about, well, you're talking about stars and planets, sounds like they're pretty far away. What about our own solar system? Can the James Webb Space Telescope actually study our own solar system? Well, it's not going to be able to look at things closer to the sun than Earth. So it can't study Mercury or Venus because of that. It's got to block out the heat and light from that part of the solar system. But it can study further out. So it could study Jupiter and Saturn, and we could help us understand more about the formation of our own solar system by what it contributes. Oh, we've got another question for you. So you all be sure to answer this to help us understand how many people are watching right now. And
I see a couple good thoughts here. I just lost my little Q&A window. Here we go. Miriam asked, why are there wrinkles on the gold mirror surface? Yeah, you might have noticed when it was in the clean room images and stuff like that, you might have seen some wrinkles and things like that. That is not intended to stay that way. It's probably something to do with how it was being tested here on Earth. As Amy mentioned, we do want those mirror segments to be as flat as possible so they can collect as much light as possible. So any little imperfections and things like that before they finally pack it up to go into the rocket should be all fixed and smoothed out. So it might have just been a product of something in that image. As far as I know, there should be no intentional wrinkles on the mirror surface.
Yeah, the mirror segments actually have little motors on them that can get them to adjust it just right once everything unfolds in space so that it all functions as one giant perfect mirror. Some of you, if you're old enough, you may remember that the Hubble Space Telescope, which has returned all these amazing images, it was actually launched with a mistake in the mirror. And space shuttle astronauts had to go fix it. And it worked amazingly well. And so it turned out really well. So they're very careful with how they put these mirrors together. And Nick, I don't know if you see anything else you have time to answer or not.
Yeah, well, Emily asked a really big question, so I'll give you kind of a short answer to your big question. She asked, how can scientists tell how far back in time they're looking? That's a big thought because we do have to wrap our minds around the fact that light takes time to travel, and some of this light is coming from really, really far away. So there's a number of ways that telescopes and analysis can figure out how far away a star is. But even when you're looking at something as close as the moon or the sun, technically you're looking at how that object looked a number of seconds ago or minutes ago. For the moon, it's about 1 light second, something like that. And then what's our light travel time to the sun?
About eight light minutes. Yeah.
So that just kind of amplify and multiply that out. If you're looking at a star that you've been able to measure is 50 light years away, that means you're seeing the light from the star as it looked 50 years ago. Now, the way that they measured that is really interesting. You can look at brightness and luminosity, how inherently bright the star is, and make some cool calculations on where it is in position to other stars. There's lots of ways to do it, basically. But we can study the chemistry and composition of these stars from their light, and we also get a snapshot of time as well from their light. So hopefully that's a satisfying answer to your big question. But it's a fun thing to explore more, just how we can piece together and make sense of things that are so far away and be accurate when we do it.
So I think we're about out of time. I want to make a shameless plug for next week, September 8th. We're going to focus on stories. Some of y'all have expressed a lot of interest in stories about the sky, and somebody specifically asked for the Perseus and Medusa story. So we are going to share that next week. So join us.
Yeah, we're excited. Greek myths, same time, same place, Tuesday at 10 a.m. Eastern. We'll be here. We want to thank you guys for joining us for Morehead at Home today. If you like this content, these lessons are going to be recorded and posted on YouTube. You're welcome to go back and watch the one about the Hubble Space Telescope and compare it to the James Webb Space Telescope. That's my homework assignment for you. But really, we're happy to provide resources. You can go to our website, moreheadplanetarium.org, check out the Morehead at Home page for some of the stuff we're doing in this time while our building is closed. And we're on social media, Facebook, Twitter, Instagram, that YouTube channel, Morehead Planetarium, as I mentioned. Check it out. We hope this inspires you to look up and think about your universe a little bit more. But until next time, have a great rest of your day.